Hello, my name is Yuval Levental. I am pleased to meet all of you today. Currently, I am a PhD student in imaging science at the Rochester Institute of Technology, presenting here at the 2024 IEEE ISPW. Regarding my educational background, I obtained my bachelor's degree in electrical engineering from Michigan State University with honors and my master's degree in imaging science from Rochester Institute of Technology. My master's thesis was lidar voxel segmentation using 3D convolutional neural networks. I have completed this current project for a class I am taking, Advanced Robust Machine Learning for Interdisciplinary Imaging Science Applications. The title of this project is Performing Different Resampling Algorithms on Image Datasets Using Deep Learning. Please contact me at yhl3051 at rit.edu. Recently, minority classes in imbalanced image datasets have been oversampled and classified using various fundamental techniques. The paper Deep Smart by Deblain et al. In 2022 is one recent example where deep learning is combined with a smart algorithm. In Deep Smart, a trained encoder converts the images into embedded vectors. The generated vector classes are oversampled using small and reconstructed into images of a trained decoder. Accuracy is determined by training a separate CNN model using the oversampled data and then running the model on provided test data. However, the authors did not test more complex resampling techniques on embedded vectors. We test 14 different resampling algorithms on 5 different image datasets of varying complexity: MNIST, FNIST, C410, ImageNet, and iNaturalist, to see which combinations resulted in the highest overall accuracy. The algorithms either directly oversample or use multi-class resampling. Overall, simpler image datasets and more complex algorithms have the highest accuracies. On to the datasets. MNIST and FNIST are sets of 28 times 28 pixel grayscale images on a black background. MNIST contains single-digit numbers from 0 to 9, and FNIST contains images of clothing. Overall, they have the least features. By contrast, the versions of C410, ImageNet, and iNaturalist, which were tested, are 32 times 32 pixel RGB images. C410 and ImageNet images were labeled according to the primary object in the image, whereas iNaturalist images are labeled according to any object in the image. All annotations were unreviewed. Figures 1 and 2 contain examples of MNIST and C410 images, respectively. For MNIST images, there are 10 categories where the images are generally composed of white lines. This makes classification relatively easy due to limited features. For the C410 images, there are also 10 categories, but the images are in full RGB color. Therefore, classification can be challenging due to more complex features. 10 imbalanced categories are created from each training image dataset. To obtain enough images, some default categories have to be merged into larger categories. Each category respectively has the following number of images in order to represent extreme imbalance: 4,000, 2,000, 1,000, 750, 500, 350, 200, 100, 60, and 40. Additionally, the category ordering is also random. After that, each imbalanced training dataset is used to train an autoencoder. The autoencoder was programmed with PyTorch and PyTorch Lightning libraries. A diagram of a basic autoencoder is shown in figure 3. Additionally, the latent vector length was set to 384, which is a sum of 256 plus 128, both powers of 2. A trained autoencoders then resample the datasets in different ways. 9 oversampling methods are based on small, which use different kinds of linear oversampling based on various features. 2 methods focused on extreme class imbalance. Finally, the last 3 methods use multi-class resampling, which focus on all the classes as a whole. They are novice distance oversampling, similarity-based oversampling, and undersampling preprocessing, and spider-free cost-sensitive preprocessing. Each resampled dataset is then fed into a CNN classification algorithm. The resulting models are then tested on corresponding dataset test images. 4 different metrics are accessed to measure overall performance. These are accuracy, which is simply the percentage of correctly classified data, the geometric mean, which is a square root of precision times recall, index of balanced accuracy, IBA, which evaluates only 2 class and balance domains, and the area under the ROC, receiving operating characteristic, which holds true positive rate as a function of false positive rate. Tables 1 to 5 show results for all the datasets. MNIST was the best and FMNIST was almost as good. ImageNet was in the middle and did quite better than CFAR10. While there were more ImageNet categories to begin with, they were selected from a far wider range of categories than CFAR10. Finally, iNaturalist has a lost performance since the images were not focused on the main category, and elements in nature tend to be more difficult to predict due to their pseudo-random nature. Multi-class resampling algorithms usually perform better than simple distance algorithms, like small. One major exception was RBCCR, since this algorithm focused on subregions of a dataset for oversampling. Overall, MNIST with RBF had the highest geometric mean of 0.976. iNaturalist with CCR has the highest geometric mean, only for the dataset of 0.292. Overall, simple datasets with complex multi-class algorithms have the best performance. In conclusion, I hope you have enjoyed this presentation. Again, if you have any questions, feel free to email me at yhl3051@rit.edu. Thank you.